So hello to you, my name is Houssam ElBouanani. I with Chadi, Barakat, Walid, Dabbous and Thierry Turletti, all from INRIA Sophia Antipolis in southeastern France. We have authored this paper on passive delay measurement for the fidelity monitoring of distributed network emulation, which I will be introducing to you in this presentation. Okay, so before we delve into it, let's start first by giving you a brief and general context about our works, that you may better understand where do the assumptions we have been working on come from. And so we have been working on network emulation, which is basically just about mixing modeling with realism. So you can do that either by modeling services and applications on top of physical networks, or by running actual services and applications on top of emulated networks. Okay, so to do that you can resort to network emulators, which are very popular, and they mostly align with this second paradigm of network emulation, as they use virtualization for nodes and end hosts and switches and routers, etc., which lets users run their actual operating system and application code, but the network emulator still models some network phenomena and components such as the network links. Okay, so let's say for example you want to emulate this simple network where one client is connected to one server through one network switch, and you want to emulate it in your cluster of two physical hosts. One way to do that is to run the client and the switch as virtual machines in the first physical host and the server alone in the second physical host. Now, okay, so far so good. Now the problem is that since these links are only modeled, they are not real links, the fidelity and realism of your emulation will only be as good as the modeling of these links. Okay, so what we do is, what we propose is, in order to ensure the fidelity and realism of your emulation, we propose to monitor these links here, and the performance indicator, the fidelity indicators we have been working with, is the network delay. Okay, so we want to monitor the fidelity of the emulation by measuring the network delays of the packets that are emulated and that cross these links. Okay, so this is the crux of our work, and which brings out this set of 5 requirements. So like I said, we want to measure the link level delay of packets, not the end-to-end application or socket level delay. And we want these measurements to be passive. So we want to measure the delays of already emulated packets, not the delay of the packets that we inject into the network. And we also want the solution to be compatible with the virtualization traffic control, which are used in the context of network emulation. And we want it, of course, to be efficient even at scale. Okay, and so this, since lately there has been a trend by using distributed network emulation, we still need our solution to be accurate and precise even in these scenarios. Okay, and so to achieve this, the delay measurement principle is very simple. We just timestamp packet transmission and reception events and log those timestamps from each network interface card, each switch port, router interface, etc. And then from these timestamps we could measure the delay at link level. So to measure it at link level and not include any added system delay, we need to timestamp transmission as late as possible and reception as soon as possible. Okay, but to include all important network delays, such as the queuing delay, we need to timestamp packets at some specific points in the path. Okay, so one way to do this is just to use already available packet timestamping tools such as libpickup, which does that very good and very efficiently. So let's go back to our example, where let's say we want to monitor the packet delays of this local link that is emulated using simple Linux vet pairs. What we have to do is, like I said, timestamp packets at both ends of the link, and then measure or estimate the one-way delay. Now, in this scenario, the client simply sends packets to the server at a rate of 1 packet per millisecond. Okay, and then we timestamp those packets and measure their one-way delay as the difference of those timestamps. So what we find is that the packet one-way delay is around 59 seconds. Okay, seems reasonable since the link is only local. Now let's add more complexity to the link by using traffic control and adding 1 millisecond of emulated delay. What we find using lib pickup is that the one-way delay we measure is still around 59 seconds, microseconds. So this is obviously a problem. So the issue is that the existing solutions to packet timestamping are not adapted. They can only timestamp the packets at some specific points of the path that are not of interest to us. Okay, so we need to program our own packet timestamper by using, for example, the extended Berkeley packet filter, which is a framework that is very efficient and powerful for kernel tracing, in that it allows users to plug their own code into some kernel routines. So for example, two kernel routines that are of interest to us are qdisc-enqueue and qdisc-dequeue that are used by the traffic control subsystem in the Linux kernel. Okay, so our solution is simply works like this. So imagine you have a machine that can be either physical or virtual, where your application sends the packets to the network interface card of the machine. But these packets, they go obviously through the traffic control subsystem of the Linux kernel. Okay, so what we do is that we intercept those packets at the traffic control level by our eBPF solution, and we compare that to libpickup that intercepts packets at the file that represents the network interface card in the Linux kernel. Okay, so when they are intercepted, they are time-stamped using the local clock of the machine, and those timestamps are sent to a monitoring program that simply just compiles all of that into a packet dump, which is a table that associates each packet or packet ID to its eBPF timestamp and libpickup timestamp. So using these timestamp, we can then measure the one-way delay. Okay, so when we do this in our link emulated using vet pairs and 1 millisecond of added traffic control delay, well, we find that using our solution, the one-way delay is the one-way measured delay is in fact around 1 millisecond, as opposed to libpickup that still does not correctly measure the one-way delay. Okay, so with this we have already checked 4 of our requirements, but we still need our solution to be accurate and precise in distributed environments. So to check this, let's instead focus on this link here, which crosses the cluster physical network and which is emulated using overlaying technologies. Here it's the VXLAN. So when we use our solution on this, what we find is that the measured delay is biased by clock asynchronization. So we find that the one-way delay increases for each packet, even though all packets are supposed to have the same delay, and they are completely uncorrelated from each other. So there should not be any difference between their delays. Here we find that their delay increases by 0.2 millisecond each second. So there must be a problem of time asynchronization, let's say. And so this problem is not new. This has been tackled many times before in the context of distributed systems. And so one solution to tackle it is just to use synchronization, time or clock synchronization technologies. So one solution is the precision time protocol, which can achieve very high accuracy and precision in a Ethernet cluster in the order of 1 microsecond, but which requires very special hardware that should be implemented into the network interface card. So this is a very awkward solution, especially since we want it to be compatible with virtualization, where the network interface card are only virtual, so no special hardware can be inserted into them. And so a second solution is to use the network time protocol, which is a kind of watered down version of the PTP, but which still can achieve very high enough accuracy and precision. But the good thing is that it does not require any special hardware. The problem is that it takes a very long time to converge. So after 2 hours of running NTP, we were able to measure a kind of stable and accurate one-way delay, which is good. And so this relies on synchronization technologies, which is an assumption that cannot be made in all settings. So it's not always possible to have synchronization. A second solution is that instead of measuring the one-way delay of individual packets, what we can do is that we measure the round-trip delay of pairs of packets. So for example, let's say in one link, one end A of a link send packet to a second end of the link, and that this end B sends a second packet P to the first end A. Okay, so here we have 2 packets that are not necessarily related. They might be part of different network flows, no problem. And so by timestamping these packets, we get 4 timestamps, and then using this formula here, we can compute the round-trip delay of these 2 packets. Okay, so it is simply the sum of their one-way delays. And so using this solution, the measured round-trip delay is very stable, very accurate and very precise. In fact, it's accurate and precise enough that we are able to infer the link bandwidth and or capacity just by varying the packet sizes. Okay, and so I say this this shows that it's very accurate and precise because the term here that increases by packet size is only in the order of few nanoseconds per byte of packets. Okay, and so with this we have checked all 5 of our requirements, which is good. And so to recap, I would say that, as we said, delay measurement is a requirement for fidelity monitoring in the context of network emulation. And this sub-problem here poses very interesting challenges. First, from a system programming point of view, in that we need very efficient and accurate and specialized timestamping. And also from a distributed systems point of view, in that it needs clock synchronization. But with the right tools and the right methodology, we showed that we are able to obtain very high delay measurement performance. And so in our free tour works, we would want to expand the capabilities of this eBPF packet timestamper we have come up with. We also want to circumvent time synchronization to abandon this assumption in the measurement of the one-way delay, and when that is achieved, to implement our emulation fidelity monitoring using delay measurement. Okay, so thank you for listening. If you have any questions, I'll be very happy to answer them.